Welcome to this explainer. Today, we're taking our view of the world from simple qualitative observations and turning them into hard, exact, quantitative physics. We are mastering the critical foundations you need for DPE 803. Because if you really want to understand how scientists decode the universe, well, you have to speak their language first. Let's jump right in.
Picture this. You're standing on a massive suspension bridge. Now, what if I told you the engineers who built it didn't even agree on how long a meter was? Sounds crazy, right? Well, back in 1999, NASA actually lost a $125 million Mars orbiter simply because one team used English units and the other used the metric system. Without universally agreed-upon measurement standards, science, engineering, and honestly the entire modern world would literally collapse. Everything we know about the physical universe completely relies on our ability to measure it accurately.
So here's our game plan for today. We're going to hit the language of physics, the SI unit system, prefixes and scientific notation, measuring instruments, errors and uncertainties, and we'll wrap up by mastering significant figures. Section 1. The language of physics. Before we even pick up a single tool, we need to define the core quantities we're actually trying to measure.
You know, in physics, knowing how much is really only half the story. Take scalar quantities. They're pretty simple, like the mass of an object or just the number of words in a sentence. They just have a magnitude, a size. But vector quantities, now they require a magnitude and a direction. If you tell me to apply a force of 10 newtons, I literally can't do it unless you tell me which way to push. Let's look at base quantities. Think of these as our alphabet. Just like you absolutely cannot derive the letter A from the letter B, you can't derive length, mass, or time from one another. We've got 7 of these foundational building blocks. Derived quantities, on the other hand, well, those are the words we spell using that alphabet, like taking length and time and combining them to get speed.
Moving right along to Section 2, the SI unit system. Now that we have our alphabet, we desperately need a universal dialect.
This is where things get really cool. Base units combine brilliantly to measure some pretty complex phenomena. Look at area and volume. They're really just meters squared and meters cubed, right? Speed simply takes meters and divides by seconds. And when things get super complex, like force or pressure, we actually give those derived units special names, like the Newton or the Pascal, just to honor the brilliant scientists who figured them out.
All right, listen up, because this is a massive high-yield fact for your exams. The grammar of SI units matters. So many easy marks get lost because of sloppy formatting. First off, symbols never ever take plural forms. It is strictly 10N, not 10S. And if you decide to write out the full word Newton, keep the whole thing lowercase. Yeah, it feels weird, but that's the rule. But if you're using the single letter symbol to honor Sir Isaac Newton, boom, it has to be a capital N. Oh, and prefixes? They snuggle right up close and directly in front of the base unit.
Section 3. Prefixes and scientific notation. It's time to step into the realm of the incredibly large and the microscopically small. These prefixes are basically a physicist's ultimate cheat codes. Let's be real, nobody wants to write out a dozen zeros every single time they do a calculation. By just slapping a prefix directly in front of our base unit, we can effortlessly express the thickness of a tiny wire in millimeters or a whole planet's distance in gigameters. Memorizing these powers of 10? Absolutely crucial. You gotta know these cold for your exams.
Now, what if you don't have a prefix handy? Well, scientific notation is your new best friend. And it's a super simple 3-step procedure. Let's take the average distance from the Sun to the Earth. 138 million kilometers. Massive number, right? But by just moving that decimal point 8 places to the left, we elegantly compress it into 1.38 times 10 to the power of 8 kilometers. Clean, standard, and so much easier to read.
Section 4. Measuring instruments. We know the math now, but physics isn't just theory on a page. Let's look at the actual lab tools we use to extract these numbers from the real world.
Before we even touch a tool, we have to know its limits, and that brings us to the least count. This is the absolute smallest, most precise measurement an instrument can accurately record. For instance, if you're using a standard meter rule in the lab, its smallest division is 1 millimeter, meaning you literally cannot measure anything smaller than that with it. It's just not possible.
But hey, what if we need more precision? Notice how the vernier calipers gently grip that solid cylinder. By using this really clever sliding secondary scale, this device lets us measure correctly up to a much finer least count of 0.1 millimeters. Pretty huge upgrade.
And guess what? We can go even tighter.
Enter the micrometer screw gauge. By rotating the thimble, we use the pitch of the screw to measure impossibly tiny thicknesses, like we're talking a single sheet of paper here. It measures accurately all the way up to an impressive 0.01 millimeters. The main takeaway: the instrument you choose completely dictates the precision of your entire experiment.
Section 5. Errors and uncertainties. Time for a hard truth about experimental physics. No measurement is ever truly perfect.
Every single instrument, and honestly every single scientist, introduces some level of uncertainty. There are three main culprits you've got to watch out for in the lab. First up, human errors. These are just our own mistakes, like misreading a scale because you looked at it from a weird angle. Then you have systematic errors. This is a flaw built right into the instrument itself. Maybe your ruler is chipped at the 0 mark, which shifts literally all your readings in one direction. Finally, random errors. These are totally unpredictable fluctuations in the environment, a sudden drop in temperature or a random gust of wind messing with your delicate physical balance. The best way to fight back? Take multiple readings and calculate an average.
This brings us to a massively important, crystal-clear thumb rule straight from the syllabus. Do not mix these up on your exam. Precision and accuracy are absolutely not the same thing. Precision is entirely about your tool. A smaller least count means less absolute uncertainty. Your results are tightly packed together. But accuracy? Accuracy is about the truth. It's how close your measurement actually is to the real accepted value, meaning less fractional or percentage uncertainty. Think of it like this. You can have highly precise, beautifully consistent measurements, but they are completely inaccurate if your instrument is broken and totally misses the bullseye.
Moving on to our final stop, Section 6, Mastering Significant Figures.
So, how do we formally and honestly communicate our precision to the rest of the scientific world? We do it using significant figures. In any measurement, these are all the accurately known digits plus exactly one estimated or doubtful digit. This rule is a reality check. It reflects the actual physical capability of the tool you just used. It actively stops us from reporting those totally misleading calculator outputs. Like writing down an answer with 10 decimal places when your basic meter rule could only guarantee 1. Let's drill down on a specific mathematical rule here, because this is exactly where examiners love to test your grasp of laboratory rigor. When you add or subtract, your final answer can only have as many decimal places as your least precise measurement. Period. For example, if you add 72.1 meters to 3.42 meters, your calculator is going to eagerly spit out 75.52. But wait, because 72.1 only has one decimal place, you absolutely must round your final answer to 75.5 meters. Your math cannot be magically more precise than your weakest measurement. We've covered a ton of ground today, from standardizing our base units all the way to communicating honest precision through significant figures. But I want to leave you with one final thought to chew on. As human technology keeps advancing, from simple wooden rulers to massive particle accelerators and electron microscopes, we are constantly shrinking our least count and reducing uncertainty. But will our measurements ever actually reach absolute perfection? Or is a tiny sliver of doubt permanently built into the very fabric of the universe itself? Keep questioning, keep measuring, and I'll catch you in the next explainer.